All right, so this is our last video for chapter 6, and we really just have one thing to finish up with our electron configurations. Make sure that you have your periodic tables handy. All right, so as we've been doing our electron configurations, we have noticed that when we are filling our D sublevels, for example, if we are adding electrons into 3D, we do 4s2, 3d, then 4p6. So we're adding electrons to the fourth energy level, then back into the third, and then back into the fourth energy level. And the reason is because 3D, even though it has the number 3 in front of it, is actually higher energy than 4s. So that's what this chart here is showing us. So what we have is these are our different energies. So 1s is going to be my very lowest energy. That's why we always fill that one first. And then energy is going to increase as we go up. So 1s is the lowest energy. We fill that first. Then 2s, then 2p, and we would add 6 electrons to 2p. Then our next lowest energy one is 3s, then 3p, then 4s, then 3d, even though it's a D, then 4p, and so on. So again, just use your periodic table. Remember that as you go across the periodic table, you just fill it based upon how you're moving. If it's a D, it's 1 behind. If it's an F, it's actually 2 behind. Okay, so we have some rules for our electron configurations. So we can only put 2 electrons in one orbital because that's all an orbital holds. Then we have some other ones here too. We have to fill the lowest energy sublevels and lowest energy orbitals first. That's what that diagram was just doing. The Pauli exclusion principle is 2 electrons occupying the same orbital must have opposite spins. We're going to take a look at that in a second. And then Hund's rule is that electrons in the same subshell sublevel will remain unpaired with the same spin until all orbitals are half filled. And we are going to take a look at that in a second here. Okay, so we are going to be doing the orbital diagram for these elements. Now, in order to do that, we first have to do our electron configurations. So chlorine, that's Cl, we got 17 electrons total. The electron configuration, 1s2, 2s2, 2p6, 3s2, 3p5. So that would be my electron configuration for chlorine. Now, what the orbital diagram is you show each orbital and how the electrons are arranged in there. So we first have one orbital in the 1s sublevel, then 2s, okay, then our next sublevel is 2p. There are 3 orbitals in 2p, so you draw either 3 boxes or 3 lines. Then we have just the 1 orbital in 3s and 3 orbitals in 3p. Okay, now this gets at those spin rules. So we have 2 electrons in 1s, so they go spin up, spin down. So basically draw an arrow up and an arrow down, showing that the electrons are going to orient themselves with different spins to minimize repulsion. 2 electrons in the 2s, opposite spin, 2p. What the seats on a bus rule was talking about was each orbital, each one of those lines gets 1 electron. Then if you need to fill it up, then you go back and fill it up. So that's seats on a bus because everybody takes a single seat. Then if you have to double up, then you double up. Okay, so 3s is full and 3p has 5 electrons. So we go 1, 2, 3, each orbital gets 1 electron, then we double up if necessary. All right, so you might be thinking, why would I need to know this? So you'll get questions about how many paired or unpaired electrons there are. So if we're looking for unpaired electrons in chlorine, we can see that we have 1 unpaired electron in there. And that will affect some other properties, especially ones that we talk about, like ionization energy in our next chapter. Okay, so let's take a look at calcium. So calcium, Ca, we got 20 electrons. So if we look at our electron configuration for calcium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, because it's in the second column of the S block, so it's going to end in S2. So now we do our orbitals, either as lines or as boxes. So 1s just has 1 orbital. We put 2 electrons in there, so spin up, spin down. 2s has just 1 orbital, 2 electrons go in there. 2p has 3 orbitals, so 3 lines or 3 boxes. We will put a total of 6 electrons in there, so those are all paired. Sorry, that arrow was a little bit messy. Oops, wrong color. There we go. All right, now we are 3s, so just 1 orbital. 3p has 3 orbitals, 6 electrons total, and 4s just has 1 orbital, so the 2 electrons in there. So calcium has no unpaired electrons. Everybody is paired up. So paired up means that there's 2 electrons per orbital. All right, last example, we've got iron. So iron, Fe, we have 26 electrons. So the electron configuration for iron, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we go into D. Remember, D is 1 behind, 3D. If we count over for iron, it is 6 over in the D block. So it's going to be 3D6. All right, so then when we go to do the orbital diagram, 1s contains 2 electrons. 2s also contains 2 electrons. 2p has 3 orbitals, contains 6 electrons total. 3s, just the 1 orbital, contains our 2 electrons. 3p has 3 orbitals. 1, 2, 3, 6 electrons. 4s contains the 2 electrons. I'm running out of space, so I'm going to have to put 3D above up here. So I'm going to get rid of some of this here. Okay, so I'm going to have to continue 3D up here. Since it's a D, we have 5 orbitals. So we have 1, 2, 3, 4, 5, 6 electrons. So what we would see from this notation, and let me again erase some of this other stuff that I've got in here so that we can focus in on iron. All right, so what I see from here is I have 1, 2, 3, 4, 5, 6 sublevels that are totally filled. I have my last sublevel that is not totally filled. I see that in my 3D sublevel, I have 4 unpaired electrons. So these ones that are by themselves are unpaired electrons. All right, one other thing that these will impact is whether or not something is magnetic. So we know that most of our metals are magnetic, but not every single metal is magnetic, such as zinc. Zinc is not magnetic because it has all of its electrons spin paired. So that's called diamagnetic. And what that means is that there are no unpaired electrons. And if there are no unpaired electrons, it will not be impacted by a magnetic field. Whereas paramagnetic means that it will respond to a magnetic field because it has unpaired electrons. So those orbital diagrams are very important for determining this. One other thing is if we have a half-filled orbital. So for example, if we have something that ends with P3, it would be half-filled. We have 3 orbitals, 1 electron in each, so half-filled sublevel. That will be a little bit more stable. So things that are half-filled have a little bit more stability and a higher ionization energy. So that will affect us in our next chapter, chapter 7, when we talk about periodic trends.